Right, so hopefully it won't take too long. I always say that. What I'm going to do is just whiz through each. Well, we'll recap on just a bit of recap on Q because we've done it several times. Though Kerry probably hasn't heard that much on Q. And then I'll just go through the various methods that they all came out of DeepMind in a flurry of activity between about 2015, 2017. So we'll have a look at just what they are so you're familiar with the names, and then I'll point to you where I've implemented them. And there's also references where the original papers and stuff are. And then I'll mention what I'm playing with the Q Hospital, and if anybody wants to play along with that, there's going to be lots of little things that can be done along the way. So I'll sort of show you what it is and what doing. It's a sort of slow project in the background. Right. So here are the Deep Q agents that we'll go through, and you got this. I'll send this out afterwards. So the original Deep Q learning actually went back to 1992 or possibly earlier. It's sort of a bit vague of who did what. I think this paper is the first one that used the sort of structure we're looking at today, sampling from a memory and such like. Then it all went quiet up until 2015. And that's when I think this was the first one that came out from DeepMind, the double Deep Q network, which we'll look at. Last author there is David Silver, who turns up an awful lot on the Google documentary on AlphaGo. He was leading the team that beat Lee Sodell at Go. Then we're going to have a look at Dueling DQN, double DQN, Prioritized Replay, Nosy, Bootstrap, Distributional, and Rainbow. Just sort of a slide on each of those. You can see it all came out really pretty quickly, and as far as I can tell, they're basically the key Deep Q methods. But I think one thing we need to do is have a bit more of a literature look, see if there are others. But these are the ones that are talked about and implemented, it seems. So when you can use Deep Q, do interrupt at any point if you want to, please. Deep Q methods are suitable for all problems where there's a choice of discrete actions to take. So that it can be any number of choices, but it has to be discrete choices. So before on the hospital simulation, what I've got is you can adjust the beds upwards by 5, 10, 15, 20 at one particular step in time, or reduce them by the same amount. So you have multiple actions, but they're all discrete choices. It's not suitable for problems with a continuous action, such as where you're going to hold an accelerator pedal, which could be a fraction. You could adjust by a fraction. You could potentially break that down into 100 steps, and then you could use Deep Q. But there are other methods that are better for the continuous action problems. I think most things we're going to be looking at will be discrete choice, I think. There's links here to the Learning Hospital, so we've published a preprint paper on this, and that site links to, I must make sure it links to the paper actually, or I'll put the paper in. And the Learning Hospital site links to all of the notebooks and gives a bit of, for each page, gives a bit more background than are in the Jupyter notebooks. And then there's the GitHub repository. Right, let's go, sorry, let's do this one first. I'll move that order. So, elements of reinforcement learning. Kerry, this is all unfamiliar to you, I imagine, is it? Are you there, Kerry?
I am. Sorry, I couldn't find the mute button. I joined one of your Q ones. I think you drew a second one.
Oh, right. Okay, so it's sort of bits of familiar.
Yeah.
Okay. So let's just whiz through this. We need an environment, which for us is either the real world we're working with, or to begin with a simulated environment where we're trying to solve a problem like a bed control problem, or thinking of ambulances at the moment also, where might they go? And you can build a model world of it and then transfer it hopefully to the real world. An observation is sensing the environment, sensing the state of the environment. So the state is the perceivable environment. Let's change this order. And the observation is what you can observe or do observe of it. Then we have our agent. That's the thing that senses the environment, decides what action to take, and it receives and monitors rewards. Actions mentioned could be discrete, it's what we're looking at, or continuous. Then we talk about policy, sometimes just called PI, and policy is basically what you do. Given the observations that you've got, what action do you take? And that's what we're always trying to optimize. We're trying to optimize our policy. Then we have a reward signal that comes back from the environment, and our aim is to accumulate the maximum reward over time. Then we have a memory. So that's each time we take an action in the environment, we remember what state we were in, what action did we take, what reward did we get, and what new state did we end up in. Then we've got three things here to do with how good a state or an action is. Value is the prediction of what reward will I get if I end up in one particular state. So value is related to the state. Q is related to actions from a state. So they're very similar but subtly different. Q sort of says, what reward will I, long-term reward will I get by taking action A, B, or C? And a large component of that is what next state you end up in. So Q and value are very closely related, but value is strictly to do with state, Q to do with action. And then advantage is the difference an action makes compared to the other choices available to you. And at in any one state, the average advantage is always 0. So you're looking at the differences different decisions can make. And then we have our target. We'll come on to that, which we've done briefly before. Okay, a reminder, this is the Bellman equation and everything hangs on this. So Q, given any state and action, equals the reward that you get from making that action from that state, plus a discount factor called gamma, multiplied by what's the best Q available from the next state. So that next state has a series of possible actions, and if you took the action that led to the best Q, that's your max Q, multiply that by gamma and add in your current reward and you get your current Q. So the nice thing is about this, it's really simple in essence. All you need to know is what reward you're going to get and an estimate of what you think the best next Q is available to you, and you build up everything through that one simple equation. So high level structure, we got our environment, which we'll be working with simulation, and then we have our agent, and the agent contains a couple of core things. It contains a memory. I put optional there, but everything we're looking at has a memory. So for every time you act, you remember what action you took from what state, what reward you got, what new state you ended up in, and whether it's a terminal state or not, which is when everything ends. And then we've got our policy network, and that's what we're trying to improve the whole time to maximize our long-term rewards. So hopefully this is a bit of a recap. So Deep Q network, a simple one, all we put in are the state observations. And what we get out is the Q for each possible action we can take. And we simply take the action with the greatest Q normally. And act, and then go round the loop again. So it's essentially quite simple. State in, nothing else, and Q comes out. The trick is learning or the policy network has to learn those cues. So what we do is we go around this, well, to begin with, we're on the right. So you've seen this before, just to remind you, to begin with, it's completely random exploration, apart from in one of the methods I'll talk about in a moment. And that you choose actions at random, you pass that action to the environment, and you record what reward came out, what state you ended up in, whether it was terminal. And you accumulate a series of sequences to put in your memory. Then once you've accumulated a certain amount of stuff in your memory, and you can decide how much you want to collect before you start training your network, you then start using the network, and you pass the state to the network. That gives you the action with the best Q. You pass that action to the environment. You get back your new state, what reward you got, whether it's terminal. You put that in the memory, and then you make a step to update the policy network. So we update the policy network every time we take an action, but we update it by sampling from memory. And we'll go through that in more detail in a second, rather than on the thing it's currently just experienced. Any questions so far? Because that was quite rattled through.
Right, all good for me.
Okay, good. Oh, and I've got note there that so we start off completely random, and then we enter a phase where we still take random actions, but with reducing frequency. And this is called the epsilon greedy exploration, which simply means over time, we make fewer and fewer random choices, down to either 0 or whatever minimum we want to set. So training a deep Q network. So this happens at each time we take an action. We might get several things from the memory, but let's just take one. So we go to our memory, and in this instance, we select completely at random. We select something that happened in the past. So what state we're in, what action we took, what reward, what new state, whether it's terminal or not. Now, taking that action, we get what's the best action from the next state, S prime, from our policy network. And then, so that tells us, because what we're trying to get, so we've got reward. If we think about the Bellman equation, it's reward plus gamma times the Q of the next step. So what we know our reward, what we're now trying to get is, well, what's Q for the next step? We get that from the policy network itself. So we get the next action. We get to where we decide on the next state, we get the action that gives us the highest Q. Now, our target for our policy network, which we're trying to get it to predict, is our target given our current state and action, which we've just sampled from the memory. What we want that to predict is the reward, which we've just got pulled out of the memory, plus our best prediction of what maximum Q is for the next state. And we get that from the policy network. We then calculate a loss between what our policy network currently predicts and what we calculate, which is our target. And using normal neural net stuff, you use that loss to update the network so it better predicts the target in future. So on the right, I've just sort of written that in a different way. So the aim of the policy network is to predict Q for any state action pair. Q depends on the reward from the state action, which we get from the memory, and the best Q for the next state, S prime and A prime. Q for S prime A prime, because we can't get that from the memory, is obtained from the policy network itself. So the policy network's actually updating itself partly based on its own predictions, which seems utterly crazy to me. And apparently one of the biggest surprises in reinforcement learning is that this works. It surprises everybody. But it turns out it's not a crazy idea. It is a genius idea, because it is, well, at least it's mostly genius. It's not perfect, which is why we come on to the amendments, but the basic idea that you can slowly bootstrap yourself up, slowly improve your predictions of Q by using the reward which you know and the best idea, best prediction you've currently got of the next Q actually works. But having training a network on partly on predictions that it's producing itself does seem a bit mad. One problem with this is that it can lead to overestimation of Q, which is where the next thing comes in. So I think this actually is the most complicated bit to get into your head, or I found, particularly the bit that it predicts based on itself. How are people feeling about it?
Having heard this a few times now, actually, it's all much clearer.
Is it start? Yeah, I mean,
I take a few explanations, but yeah, no, I'm actually going, oh right, yeah, no, totally understand that, and this reinforcement component within where it's using the policy network.
Yes.
That is the reinforcement a good choice.
Yes.
In a way. Yeah.
Good. Okay. Right. So a problem we've got here is if we take, if we update the network, so we're taking Q for the next state action pair from the policy network, and then we update the network. It turns out that we get this overestimation of Q. That can be avoided by using a target network. Now, the target network is a copy of the policy network, but it always lags behind, apart from once every so often when it's the same. So you copy the policy network. Now, and this again slightly odd. So we get our state action reward S prime T from memory. We use the policy network still to predict what's the best action to take from S prime. So we use the policy network for that, but we get the Q for that chosen action from the target network. And so our target network kind of lags behind being updated with these values of Q. So they will tend to be kind of lower, if you like, if we're always looking at positive Qs. And that using that sort of delayed knowledge of Q solves a lot of problems. For reasons.
It's basically saying, Mike, you're basically saying that what happens is you run the same network twice, but the second one is lagging behind the first one.
So they exist as independent networks in the program, but one is identical. They're identical structure, and every say 100 or 1,000 steps, you simply copy across the policy network. You copy all of its contents through to the target network, and that's what you use. Now the target network is never updated apart from that once every so often copied across. So there's no normal neural network updating on the target network. It's simply, you simply make a copy of the policy network, say every 100 steps, you freeze it like that while you carry on using and updating the policy network. And then you bring the target network up to date in another 100 steps. And that is enough to solve some of the problems with a normal deep Q network. So the rest is identical. So we get our Q for our chosen action from our target network. We now got a target Q that we're trying to predict, and that's the reward plus again our gamma times what is the best Q from S prime. And we want our policy network to better predict that. So we put in our state and action into our policy network, get a prediction, compare that to the target. Our loss is the difference between the predicted and target. We update our policy network to better predict the target next time. And so you go that through those steps every time you take an action, but again, we're sampling from historic memory of actions. And then we do this trick of copying. There's another trick you can use which sort of just keeps it always a little bit lagged behind. You kind of, with each iteration, you pull the target network a bit closer to the policy network. But most people seem to use this, just copy it across every so often. So that's double deep Q. So from that point, once they discovered that double deep Q solves a lot of problems in deep Q learning, basically everything sort of has these mirror target networks to help. So whatever network structure we talk of now, there's an identical target network that's copied across from the policy network every so often. So dueling double deep Q, D3QN, I might have mentioned this one before. It does the same in that well, they all do. It predicts. You put in a state, it predicts Q, but in the middle of the net, it actually divides Q up into two different things: the value of the state, which you can think of as the mean Q for all actions, and then the difference that each action makes. And it's called the advantage. And so some will be negative. So, you know, some compared to the average value of the state will be, it will reduce, and other ones will increase. So the idea of the advantage is that it focuses solely on what difference the action makes compared to others. And they always average 0. You set the network up to make sure it has to equal 0 at that point, the average. So the output is still Q, but by doing this trick of splitting it in the middle, I don't know why it's called dueling, it's not really dueling. By doing this trick of splitting it in the middle between value and advantage, you can get improved discrimination between actions, and it can learn faster. It sort of basically almost sort of says that value doesn't matter. Or, you know, what I'm really interested in is the differences between the Q values, which is the advantage. So split in two, and then we have an aggregator which simply adds them up together, and we output Q. Any questions on that one? I mean, if you ever play with these, hopefully you know, you can then sort of see these summaries. So the next one is a reasonably easy adjustment to make, and it's called a prioritized replay double deep Q network. And the principle is predictions that you got wrong in the past between your policy and target network make for better training examples, better use of your time, compute time, if you like, than retraining a network on something it predicted well anyway. So we simply amend the memory. So the memory now contains two things for each step you take. So it's got our normal state, action, reward, next state done. So that's what we always remember in a memory. And now we've got this other thing called priority.
Oh, hi, Sash. Yeah, I'm all right, thanks. I think Jackie's asleep.
And I'm mute, Andy. Oh, he's gone in. The memory steps are then sampled in proportion to their priority. So with a slight tweak, you add a tiny fraction to make sure that if something's got a priority of 0, it still has a slight chance of being sampled. And the priority is simply the loss when training the network. So the loss is the difference between what you predict and the target that you calculate. And so when the policy networks predict something quite different, that step is more likely to be sampled again. And when if the network's made and you know, it's made a perfect prediction compared to what you think it should, it'll hardly ever be sampled again. So the priority is simply the loss. And so when you take the steps out of the memory, you train the network, and you recalculate the loss that you've got, and you put that back in with that you amend the priority in the memory according to the new loss. So the principle is simply, and you can use this this technique can be used outside of reinforcement learning as well. The principle is simply you get more value out of training on things that you've got wrong. And you see it in other completely different techniques as well, like boosted random forests. You go back after training your random forest, you basically go back and say, which ones did I get wrong? And then you retrain on those samples. So it's constantly looking at what you've got wrong and trying to better predict. How's that?
That all makes sense to me.
Okay, good. Noisy. Right, noisy is not too bad. We know each, you know, in a network, we've got lots of weights. If you kind of remember your basic neural network structure, you know, all the neurons are connected to every other neuron, and along those you've got a weight. Noisy is a nice little trick in that let's see if this works. Oops. No, I'm just trying to find out how I can use a pen. Perhaps I can't. Oh well, never mind. I'll work that out some other time. So normally our weights are just these purple blobs, if you like, and there'll be hundreds or thousands of them in the network. You know, it's what connects everything to everything else in a network is a weight. You multiply the inputs to a node by the weight, and then you sum them up and send them to an activation layer. What a noisy network does is for every weight you have something that produces random noise, so Gaussian noise, simply random with a normal distribution centered on 0. And then a weight, which is basically how much to multiply your random noise by, which you add to your input. And then your output, rather than just being the normal neural network, multiply your inputs by your weights. Now each weight has this noise added in with how much noise to add. And I mean, I constantly amazed people think of these things, because it's in a way so simple. In another way, well, it's just brilliant in that the important thing is this green, how much noise shall I add, is part of the back propagation in error in the network, in that if by adding more noise I improve the accuracy of my predictions, the network will choose, making it sound a bit too human, that the network will be driven to introducing more noise into the system. And that's going to be especially true when predictions are bad at the beginning. And as the predictions naturally improve, then the noise, having this noise won't help. So it starts to reduce, it will naturally reduce the noise. So, and you know, nice thing is you just copy the code for a noisy layer, but essentially it's just every weight has how much noise shall I add, and that how much noise shall I add, you always has a sort of random input to it, and then an amount, a weight of how much shall I use that randomness in, and you combine the two and it goes to the activation layer. And this aids exploration around the place, and then it will just, while it helps to have a noisy network, it will keep the noise in, and as the network improves, the noise will naturally be reduced out by back propagation. You'll get reduced errors by having lower noise. So that's noisy. And so you can actually get away with no epsilon greedy. You still have a sequence at the beginning that's completely random. I found if you didn't have that at all, it didn't work well enough, but you only need a little bit, and then you can shut off any random selection, and it will just, it will effectively add noise while it helps. How's that one?
That's very cool, that. Yeah, in sequential sampling models in psychophysics use Gaussian noise to introduce fluctuations in the system. I've heard of Gaussian noise being used before, so the concept, and I like the way it's naturally linked into that back propagation. That's fantastic.
Yeah, it's clever, isn't it? Apparently, just adding it to classification networks can also help classification networks sometimes as well. So it's not limited to reinforcement learning, but yeah. So
cool.
It seems neat because it reduces your hyperparameter tuning. So I think anything that does that is good. It's got to be helpful.
It has, yeah. It's one less thing to set amongst many things to think, oh, what shall I have there? Yep. Right, distribution or categorical DQN. I haven't actually got this working yet. In fact, I only got it once running without it actually giving me an error, and then it just produced nonsense. So this is fiendish to implement. The principle is, if we look on the left here, this is time that it might take to go to work. You know, I don't know what, this is just stolen off somewhere. And so this is a bimodal distribution. And imagine we're trying to kind of define the value, a reward function that depends on this time. If we take an average, we're sort of kind of going to be wrong all the time, because the average is kind of close to the dip between the two peaks. So what distribution or categorical DQN tries to do is it actually tries to work out this distribution of value. So maybe sometimes an action, you know, 3/4 of the time an action will produce a value around here, and another quarter it produces a value around here. The way it's most commonly used is to say, well, I'm going to take the most likely Q, and because it's a distribution, you say Q is this point here. I'm going to say Q is my average time that I'm going to use to calculate Q, if you like, is 35 minutes. So rather than the network producing a single Q, it produces a vector, they seem to call it a support, of likelihoods across a series of bins, except they call them atoms, of Q. So it won't actually be commute time. We might have Q ranges from 0 to 100 or whatever. You divide it up into, say, 50 bins that they call atoms, and you get it to learn the distribution across that. So the aim is for it to be able to cope with complex patterns and avoid using means when you've got complex patterns, that you can say actually what's most likely to happen is here. But you could also perhaps do something more clever with this distribution than taking the most likely. People tend to use the most likely. I'd like to talk more about it, but I haven't got it to work. It's horrible.
With something like that, Mike, it's like, you know, with that commute time, it's likely you've got people using different ways of getting to work.
Yeah, it could be. So, you know, yeah, it could be that you know, that the one on the right could be people taking the train, or, you know, and you don't know whether somebody's going to take the train or take their car, whatever. But apparently it's quite good, this, if you can get it to work. This is another way, which is much easier, though computationally more expensive, which sort of does something similar. This is Bootstrap aggregating. which is commonly called bagging, and it's used a lot in different kinds of networks. In reinforcement learning, you have 5 policy networks, or 10, whatever you want. Each has its own mirror target, and you bootstrap sample from the memory. And so each network's being trained on a different random sample from the memory. And this, not surprisingly, gives you a variation in estimates of Q. That variation, particularly early on, will be wide. You would hope as the networks get better predictors, they will coalesce to a more common Q. And then you can, when choosing your action, you can either just pick a network at random, or you could say which action is most common. And you can also sort of see how different the predictions are. You know, gives you a sense of how sure am I that this is the action to take. So you've got a measure of uncertainty there. So there's a nice example that the paper, and so it's all DeepMind. They put a nice video of it playing Breakout, where it has to knock blocks out. And actually, where there's most uncertainty, it was at times it just didn't matter what it should do, what it did, because the ball that it had to hit was a long way off. So basically, it could wander around anywhere, and then later on, when the ball was coming back towards it, it needed to be certain of which direction to go in. So, and I think that was a nice example that uncertainty isn't necessarily bad. Sometimes it just doesn't matter which action you take, and this sort of pulls that out as well. So it aids exploration, provides an indication of uncertainty. It's very easy to implement, much easier than distributional.
All right, puppy dog.
And then I've put here, sometimes rather than it being completely separate networks, if you've got part of the network that you think there's no advantage in separating, so in playing Breakout, it could be those first layers, which is sort of you just give it an image of the screen, it's working out where the ball is and where the bat is and things like that effectively. It can you can have a network that shares all of that and then splits into 5 or 10 different, what they call heads later on. So it can be, I just mentioned this in case you read anything about it, that it can be a single network with multiple heads, in which case the first layers that are shared, they think there's no advantage in separating them out. And it's the later layers which decide on the policy that they separate. Nearly there. In fact, I think we're basically there. There's Rainbow DQN. And Rainbow is simply a combination of double, dueling, prioritized replay, noisy, and distributional. And not surprisingly, when you combine them all together, I don't know if it's surprising or not, I don't think it's that surprising, you get the best performance.
So Mike, can I ask how they're combined? Are all the components within a single model, or are they doing something different?
No, so it's very easy. You know, you got double, dueling. I mean, everything's a double anyway, effectively now, and nobody uses. So dueling, you add that separation of state and advantage, of state value and advantage. You'll use prioritized replay when you come to sampling the memory. You'll add a noisy layer in there, and you can make all the layers noisy, or you could just make 1 or 2 of the layers noisy. And the output in Rainbow is a distributional output.
Did bagging come after Rainbow, or did Rainbow decide not to include bagging? Do you know?
Rainbow decided not to include bagging. They mentioned that future work, try that. So it was, I think, a case of, look, we've got all these things, let's play with them. So they mention about future work putting with bagging. So I've combined them all with bagging.
Okay.
Because I could do that. Right. TensorFlow Agents, just so this seems to be quite a new library that's developing quickly. It's not complete at the moment because it hasn't got Rainbow in it, hasn't got bagging. Can't remember if it's got noisy or not. But I think if we're interested in this, worth keeping an eye on what they're doing. I mean, I'm using PyTorch at the moment for everything rather than TensorFlow, but there's this TensorFlow library that they're building, and with an associate, and you pip install TF agents, and you can see here the agents they're building. So not just Deep Q, QN ones. And they're putting things like the gym environment in there, Cartpole and Atari and stuff. So they seem to be building this up, pretty active. You can see here in the agents 3 days ago, 2 days ago, lots of commits going to this at the moment. So in DQN at the moment, they've got, oops, just a plain DQN. I thought they had distributional at some point. Perhaps I saw that somewhere else. Anyway, it's worth keeping an eye on. If you want to use that at all, it's pip install. It does require the latest TensorFlow. Conda tends to be very, well, not very, bit conservative on the versions that it has to make sure everything's working together. And TensorFlow agents won't work on the current TensorFlow that's installed with Conda if you use Conda to install it, so pip install TensorFlow. Right, last bit. Oh, well, any questions to that point? Rattled through.
It'd be interesting to see what the performance of the TensorFlow agents are in terms of execution time.
Yeah, I imagine they're going to be good.
Okay.
Because they're written mostly by the Google people who will know how to construct the back-end stuff well. But we can try it, yeah, because we saw vastly superior performance of PyTorch to TensorFlow. I mean, AlphaGo and AlphaZero, StarCraft Zero, whatever they're calling it, that's all TensorFlow. So I think they would have finely tuned this. You look at the agents, they're more complicated, definitely more complicated than the examples I've written, because they've got all these tweaks and stuff in. So I think when it comes to doing it, you know, if we try and attract some money, we might want to say we will look at these as well, because these are probably production ready agents, except not at the moment. Right, so what I'm currently working on, just kind of in bits of time that are available, and if anybody wants to get involved, is, so we've got the very basic model, which is a hospital bed model that it's controlling in the simulation. So to expand that out to a whole hospital model, so the hospital is what the agent interacts with. So the hospital has these, so these are the key steps that we always have to have. We have a reset method, a step method, render if you want to display in some way, calculate reward method, and the hospital needs to hold the overall state. So the agent only talks to the hospital. The hospital itself has no patients in, because they are either in an ED component, an ICU component, a surgery component, or object, I should say, and a wards object.
Yeah, can you do exactly the same thing?
Then we've got a whole lot of data. I've pulled data just out of HES for this, for Plymouth Exeter and Torbay. We've got ED patients by age group, whether they require admission or not, which is basically the only sensible way of categorizing them in any reasonable form from HES data, and arrival time by hour, weekday and month. And we got those arrivals separated by age group and whether you require admission or not. And then hospital admissions are split by clinical group. I've used the SUS4 HRG group. They're about, I can't remember how many of those are, 20, 30 something different groups. So it's kind of like not too big, not too small way of dividing patients. 3 age groups, whether they're emergency, elective, medical surgery, arrival by weekday or month, length of stay breakdown by clinical group, age group, emergency, elective, and medical surgical. So slowly trying to build up a simple model that or as simple as possible, that has some sensible stratification of patients going in and out of this imaginary hospital that's going to look something like Plymouth Exeter or Torbay. So what I have is the framework. I have the hospital, and it does actually reset, it does actually make steps. It doesn't return a sensible reward at the moment. And I've got arrivals at ED at the moment. Have I got them at ED? Can't remember whether they've got ED or the main hospital. Actually not by any kind of distribution of week or stuff. So it's right at the beginning. And so if anyone is interested, this can't be a major part of anybody's work because it's kind of fitting it in. So we're trying to get a paper and bid in by the end of the year. What I'd like to do is for the simple learning hospital, add in replication and summary of the replicates to see whether those models actually behave, those agents behave differently on a simple system. I need to add distributional DQN, that's not easy, and apply TensorFlow agents, or there's another one which is OpenAI, one of Elon Musk's companies, what they call baseline agents. And they, I think, are ahead of TensorFlow in creating good agents that you can kind of just take off the shelf-ish. Then the Q hospital, we need to build the ED object. That could also be a standalone model that we could get to interact with an agent, build the wards, surgery, ICU, basically build everything, integrate it all, get it to talk to the agent. Actually, that's sort of done. And adding a forecasting input, I thought, Tom, to the agent, or include some kind of forecasting within the network itself. And then ought to do at some point a bit of a review of actually what other deep reinforcement learning methods are there out there that we perhaps ought to get some simple examples working for. Right, that is all I was going to talk about. So, I mean, the main aim was just to sort of say, look here, just so you're familiar, if you're interested in this area, these are the main Deep Q network methods that you'll hear bandied about, you know, noisy stuff and things. So hopefully, I mean, that was a bit talky, but hopefully it wasn't too dull.
Thanks for that, Mike.
Thank you, Mike.
And then just let me know if anybody's interested, but don't feel any pressure because you'll have to do your day job as well.
Yeah, no, I'm definitely keen to be involved. That'd be really interesting. To do some nice applied example.
I think then hopefully it starts to sort of, you can start to think, where else might this be applicable? Everything. So what the people involved in reinforcement learning seem to stress is every problem can be solved by a reinforcement learning problem. Not necessarily efficiently, but, but everything is amenable.
Yeah.
Because we've also got some, it's solving some travelling salesman problems, which I think we looked at briefly before. Can't remember. So yeah, so I think it's useful to have an understanding of a general understanding, because I think, I could be wrong, I think these things are going to get more and more used over time.
Yeah, definitely.
And hopefully not all under the control of Google. Right.
Super.
On with the rest of the day.
Thanks, Mike.
You're welcome. See you all.
Yeah, see you later. Thanks for that. Have a good one, guys.
Bye, Sean.
See you later, everyone. Cheers.
Bye.
See you later, guys.